Good afternoon, students. We'll start our last concept of Fourier series, that is practical harmonic analysis. Practical harmonic analysis. Okay. Up till now we were given a separate function f of x, and we were finding its Fourier series. Okay, a0 by 2 and summation terms involving Fourier coefficients. Okay, so f of x was explicitly given. In practical harmonic analysis, what we are going to see is given some tabular data. Okay, given some tabular data, that means some xi and corresponding from yi. Okay, corresponding yi. Okay, this y is nothing but f of xi. Okay, so such values will be given to you, and then it is asked to find out Fourier series. I mean, first few Fourier coefficients for this tabular data. Okay, that means a1, a2, a3 and b1, b2, b3. These values can be asked from this data. Okay, so let us write. Given tabular values xi, comma yi, I running from 0, 1, 2 up to say m minus 1. How many points are there? Total m points. Okay, 1, 2 up to m minus 1 and this 1 point. So total number of points are m, where xi's are equispaced. Xi's are equispaced in the interval say 0 to 12. Okay, all xi's values are equispaced in the interval 0 to 12. Divide this interval, divide 0 to 12 into m sub intervals. Okay, m sub intervals. Divide this interval into m sub intervals. Length of each sub interval let us take it as delta x is 2l upon m. Okay, 2l upon m, 2l minus 0 upon m. Alright, and we denote it by delta x. That means next value minus previous value, and that is denoted by delta x. Okay, so divide each sub interval into divide 0 to 12 into m sub interval, and each of sub interval has length 12 by m. Okay, so what we have? So we have a0 is equal to 1 by L 0 to 12 f of x dx. Okay, when f of x is given, we have this definition, but in our case we have, in given situation, a naught equivalent definition is 1 by L. Okay, this summation integration will be replaced by summation I running from 0 to m minus 1 f of xi I r yi, and this is delta x. Okay, writing this integration in terms of summation. All right, this is one and same, so let me write approximately, because here we are taking very smallest subinterval having dx tends to 0. Okay, so this is more accurate, so we should write approximately equal to. Then a naught is equal to 1 by L summation yi I running from 0 to m minus 1. Delta x is 12 upon m. Okay, delta x is 12 upon m. So a naught is equal to 1 by L is 12 upon m is out, 12 upon m is out. What you have is summation yi I running from 0 to m minus 1. Okay, so this will get cancelled, L will get cancelled. You will have a naught is equal to 2 times summation yi I running from 0 to m minus 1 upon m. Okay, so this is formula. So a naught is equal to 2 into mean of yi. Okay, because summation yi upon m. Okay, how many yi's are there? M. You are dividing by m, so this is mean value of all values of yi. So a naught is 2 into mean of yi. All right, fine. If you do similar thing for an, what you will get is similarly an is equal to 2 into mean of yi into cos of n pi xi upon L. ठीक है, और an is equal to 2 into summation yi into cos of n pi xi upon L divided by m. Okay, where I running from 0 to m minus 1. Okay, on similar line you can prove it. Whatever we did for a naught, you can do for an. Write down formula for an in integration, I mean for Fourier series, whatever an we have stated, and use that an to get this value. Okay, or get this expression. Then bn will be bn will be 2 into mean of yi into sine n pi xi upon L. Okay, so or Vn is equal to 2 into summation yi sine of n pi xi upon L divided by m. Okay, and here m running from 0 to m minus 1. Alright, so this is third formula which I have defined in general for L. Okay, so next let us define it for particular value of L. So let xi, yi are given points where xi's are equispaced in the interval 0 to 2 pi. Okay, so what I am taking, 2L is 2 pi, that is L is pi. Okay, I am writing particularly. So A naught becomes 2 into summation yi, I running from 0 to m minus 1 upon m, that is 2 into mean of yi. An becomes 2 into summation of yi cos of n pi xi upon L, but L is pi, so that gets cancelled. So cos of n xi upon m, where I running from 0 to m minus 1, which is equal to 2 into mean of y cos n xi. Okay, y cos n xi, and Bn becomes, and Bn is 2 into summation yi sin n xi, I running from 0 to m minus 1 upon m, which is nothing but 2 into mean of yi sin n xi. Okay, so this Fourier coefficients can be found using this formula. So this will be more clear after example. So let me finish theoretical part first. Let me put into note that a1 cos x plus b1 sin x is called as first harmonic. A2 cos 2x plus b2 sin 2x is called as second harmonic. and a3 cos 3x plus b3 sin 3x is called as third harmonic. Alright. Why I have stated this? Because a question can be asked, find the Fourier series expression for the given tabular data up to second harmonic. Okay. If it is up to second harmonic, then you need to find a1, b1, a2, b2 and a0. Okay. If it is asked to find out up to third harmonic, then you need to find a0, a1, b1, a2, b2, a3, b3. Alright. All these 7 coefficients we are supposed to find. Okay. So let us solve one example. So question is, express y as a Fourier series. Express y as a Fourier series up to first 2 harmonics. First 2 harmonics. Alright. And data is given as x and y. X is 0, 60, 120, 0, 60, 120, 180, 240, 300, 300 and 360. Okay. So and values are 1, 1.4, 1.9, 1.7, 1.5, 1.2 and 1. Okay. Now very important point here is, this is periodic of period 2 pi. You can see it here, that is 360. So in some cases they may not provide you this 360 value. Okay. Alright. And you can understand looking at this table that there is a difference of 60. So next is 360 and it is periodic function of period 2 pi. So value at 0 should be same as value at 360. Okay. So even if it is not mentioned in some example, still you can write this last value which is same as first value. Is that clear? Fine. So all these examples are need to be done in a radian. Okay. So these angles you should write in radian. So 0, pi by 3, 2 pi by 3, pi, 4 pi by 3, 5 pi by 3 and 6 pi by 3, that is 2 pi. Okay. So whatever calculations we are going to do, that we are going to consider the radian angle. So you want Fourier series expansion up to first 2 harmonics. That means you want y is equal to a0 by 2 plus a1 cos x plus b1 sin x, then a2 cos x cos 2x plus b2 sin 2x. Alright. So total there are 1, 2, 3, 4, 5 coefficients you are supposed to find. Okay. So for each of the coefficient there is formula. So let us write it. What is A naught? A naught is 2 into mean of y. A1 is 2 into mean of y cos n pi x upon L. L is pi. So y, n is 1, yi cos xi. B1 is 2 into mean of yi sin n. N is 1. Okay. This n is 1. So we are putting n is 1 here. A2 is equal to 2 into mean of y cos 2xi, okay, because n is 2, and b2 is equal to 2 into mean of yi sin 2xi. Okay, so these 5 formulas are there. You need to make a proper table for this, that we'll see on the next slide. Okay, so table is x, then y, then you need y cos x, then y sin x, then y cos 2x, y sin 2x. All right. So x is 0, then pi by 3, 2 pi by 3, pi, 4 pi by 3, and 5 pi by 3. Okay. See, next is 6 pi by 3, that is 2 pi, but you are already considering value at 0, so don't consider value at 2 pi. Okay, so how many data points are there? 1 2 3 4 5 6. Okay, so value of m is 6. Okay, 2l is 2 pi and L is pi. All right, I repeat, you are considering value at 0, so don't consider value at 2 pi, and therefore these sub intervals are 1 2 3 4 5 6. Okay, so corresponding y is 1 1.4, 1.9, 1.7, 1.5, 1.2, all right, 1.2. So you need mean of y, that means you need sum of y. So this summation I have already done. Let me mention. Anyway, that can be done. Then y cos x I have already calculated. Y into cos of this angle. So that becomes 1. This is 0.7 minus 0.95 minus 1.7 minus 0.75 and lastly 0.6. Okay, so to calculate a1 you need its summation, so you can do it. Then y sin x is 0, 1.2124, 1.6454, 0, minus 1.2990, minus 1.0392. Okay, then to calculate b1 you need its summation. Then y cos 2x is 1 minus 0.7 minus 0.95, 1.7 minus 0.75 minus 0.6. Okay, you are using this x, okay, and this y. So to calculate a2 you need its summation, so you can do it. And y sin 2x at the end is 0, 1.2124 minus 1.6454, 0, 1.2990 minus 1.0392. And to calculate b2 you need its summation. Alright, so you have got all this summation. Okay, and m is 6, 12 is 2 pi. So let us calculate those Fourier coefficients. So if you calculate it, you will get a0 is equal to 2.9. Okay, then a1 is minus 0.367, b1 is 0.1732, a2 is minus 0.1 and b2 is minus 0.0577. Okay, because you have already got those summation, you just divide by 6 and multiply by 2, you will get this Fourier coefficients. So at the end you need to write Fourier series up to second harmonic. So Fourier series up to second harmonic. So Fourier series up to second harmonic is y is equal to a0 by 2, so 2.9 upon 2 plus a1 cos x, so minus 0.367 cos x plus b1 sin x 0.1732 sin x plus a2 cos 2x, so plus a2 is minus 0.1 cos 2x plus b2 sin 2x, so minus 0.0577 sin 2x. Alright, so this is what we want. So similar type of examples you can do on your own. Okay, so with this we come to the end of Fourier series, and we'll have some sessions on WebEx. There I'll solve some queries regarding this. Okay, thank you.